All right, guys, we're going to talk about optimization. And basically, optimization is using calculus to solve real-world problems, okay? So basically what we're trying to do is we're trying to use our applications of maximums and minimums, and we're trying to apply that to real-world applications. So, for example, say you were making a corral for your cows, and you had 100 feet of fence. Well, 100 feet of fence probably wouldn't be much for cows, so maybe you're fencing in goats. I don't know. Anyway, you have 100 feet of fence, and you want to make a corral out of it, right? And so you're trying to figure out what's the maximum area that I could make that would fence in my cows with 100 feet of fence. So we're going to use calculus to solve these problems. We're going to use derivatives and maximums and minimums to find the maximum and minimum of these problems. If you're interested in that fencing example, actually in our calendar, in the extra practice column, I think it's the green column, there is a video named Professor Leonard Video. He's a fantastic teacher, and he records his entire lecture, which is like an hour and a half long, and he explains things step by step by step. And so it's really good if you want more. He's a great place to go, and there's a link on the calendar. But basically, this is what we're going to do with derivatives. We're going to find two equations, one of which is going to be our equation that we need to optimize or maximize or minimize, right? So oftentimes we're talking about profit, right? Companies want to maximize profit. They want to minimize expense, right? And so a company might use this to decide how they're going to maximize their profit or minimize their expense. So we're going to have two equations, one of which we're going to be maximizing or minimizing, and another one's going to be like a secondary equation that helps us, okay? Then we're going to get everything in terms of one variable by plugging the second equation into the first equation, and then we're going to take the derivative, set it equal to 0, and find the critical numbers. And that will tell us our max and min points for whatever application. So I know it's going to seem kind of like a lot, but that's basically our 3 steps, is make 2 equations, plug one equation into the other, and then find the critical numbers by setting the derivative equal to 0. Okay, so let's take a look at what this actually looks like in a problem. So here's our first problem. We have a box, and it's going to be made, it's a box with no lid, it's going to be made from 48 square centimeters of material, right? So this is something that companies would do all the time. They say, hey, we need a box and we only want to use this amount of material. What's the biggest possible box that we can make with that amount of material? So they want to maximize their volume with the amount of material that they have. So our first step is we're going to figure out what equations we're talking about. Now remember, our primary equation is going to be the thing we're going to maximize or minimize, right? So, actually this is step number 2. The first one is to choose variables and draw a labeled figure. So I should probably do that. Let's go ahead and do that. We're going to label this figure. And so we have a box. We know it has a square base, which means this is W. If this is the width, this is also the width, right? Because it's a square base. And then this is the height, okay? So that's our labeled figure. You always want to draw a picture if you can. So the second step is to write our primary equation. So again, we're going to find what we're going to maximize, and we want to find the maximum volume with the right amount of material, right? So our second equation, our second step, is to write a primary equation. So our primary equation is what we're trying to maximize. What are we trying to maximize? We're trying to maximize volume. We're trying to get the most possible volume. So it's our volume. What is the volume of this figure? Well, it's length times width times height. Well, length is W, width is W, and height is H, right? So our volume equals W squared times height. Okay, so that's our primary equation. we're trying to maximize. Then, typically we're going to have a second equation because, see, okay, in related rates, remember we were talking about rates. So rates have to do with time, and so we could do implicit differentiation. We could implicitly differentiate. We could have two variables in there. We could have a W and an H, and we could just derive each one. In optimization, we can't do that. Okay, in optimization, we need to have it all in terms of one variable on each side, right? Only one variable on each side. Okay? And usually we're going to have a second equation to do that. Like I said, we're going to get two equations, plug one into the other. Because if we don't have that second equation, right now we have a W squared, we have an H, and we have a V. We can't derive that because we have to have it explicit. So, our secondary equation, this is step number 3, our secondary equation would have to do usually with our constraints. Okay? So we have constraints because we live in a world where it's not like we just have an infinite thing, right? If I said, like, produce a box with the maximum volume, you'd be like, all right, well, the width is 1,000,000, and the length is 1,000,000, and the height is 1,000,000, and that's a huge box, right? Like, yeah, that would be a maximum volume compared to other, like, that would be a big volume, right? But we can't just make a box that's 1,000,000 by 1,000,000 by 1,000,000. We have to make a box that lives within the constraints that we have. So oftentimes we're going to be using constraints. Hang on. That was my 5-minute bell for my prep. Let's see if we can finish this. Okay, our secondary equation has to do with our constraints, okay? So what are our constraints? Well, our surface area can be no more than 48 square centimeters, right? We can't use more than 48 square centimeters of material, and that means our surface area can be no more than 48 square centimeters. So what is our surface area? Well, it's width times width, that's the bottom of the box, right? So it's width squared, that would be the bottom, and this has no lid, so we don't have to worry about the top. And the sides, the area of each of the sides would be W times H, right? Because it's width times height. And there's 4 of those sides, right? So 4 WH. And how much can that equal? Well, at most, it has to equal 48. All right? So now we have 2 equations, and we're going to use one equation, we're going to sub one equation into the other so that we have our primary equation in terms of one variable on each side. Okay? Now, do I want to solve this secondary equation for W, or do I want to solve it for H? Well, I really don't want to deal with a square root, and to solve for W, I'd have to take a square root, so I'm just not going to do that. So we're going to solve for H. So I'm going to subtract W squared from both sides, and I have 48 minus W squared. I'm going to divide by 4W, and H equals 48 W squared over 4W. And that's probably behind my head, so you can't see it. There you go. All right, so there's our 2 equations. We're going to go ahead and solve, sub one back in. We're going to take this, wherever we see H, we're going to put this. So we're still in step number 3. So this is volume equals W squared times H, which is 48 W squared over 4W. Okay, and so then now we have, right, sub that in, okay? Now we have our volume in terms of one variable, right? Let's go ahead and simplify this a little bit because it's a little too complicated to derive right now. So we multiply, let's see, we multiply this in and we get 48W to the 4th over 4W, and 48 divided by 4 gives us, I forgot a negative sign. That's minus. I'm like, man, that is not turning out like I wrote it down a minute ago. Okay, so this is one of our W's cancels out. So we have 48W minus W cubed over 4, and we could simplify this into 12W minus 1/4 W cubed, so we don't have to do any quotient rule or anything. Okay, So this is our volume, right? We have our volume. Now that's through step number 3. The next step would be to actually maximize this, right? We want to find the maximum possible volume. And this is what our volume is. So how do we find a maximum? Well, we derive it and set it equal to 0. So this is step number 4. Oh no, step number 4 is finding the domain. Okay, so we first need to find the domain. So what's the domain of this? Well, you look at this and you say it's a polynomial, so it can have any domain, right? It can take on any value. But can it really? Can we have a negative volume? Can we have a negative width? We can't. We live in the real world, and the real world says we can't have a negative width. It's not possible. So we know that our width has to be at least bigger than 0, right? Our width can't be 0. And what's the biggest possible width we can have? I mean, we can't do anything bigger that will give us anything bigger than 48 square centimeters, right? Well, so if you think about the bottom of that box is W times W. So the very biggest that W could be would be the square root of 48. Because then when we multiply square root of 48 and square root of 48, we'd have 48 square centimeters. So W has to be somewhere in between 0 and the square root of 48. Okay? Now, so this is step number 4. Now we get to derive. Okay? So, dv dt, just kidding, not dv dt. See, I'm in like related rates. V prime equals 12 minus 3/4 W squared. I'll pause right there and I'll come back after class. All right, let's try this one more time. So here we have our derivative. Our derivative is V prime equals 12 minus 3/4 W squared. So this is how fast the volume is changing, right? This is the rate of change of the volume. And we're trying to figure out when is this at a max? When is the volume at a max? Okay, so our volume is at a max. Our volume is at a max when the derivative equals 0. Okay, say that again. Our volume is at a max when the derivative equals 0. So I'm just going to go ahead and set this equal to 0 and solve. So I subtract 12 from both sides, multiply both sides by negative 4/3, and I end up with 4 times 4, which is 16, W squared. So W equals 4. Now normally when I take the square root of something, I need a plus or minus, right? I need plus or minus 4, but we're living in the real world. Can the width be less than 0? Absolutely not. We can't have a negative 4, so that one doesn't work. So my only option is 4. My width is 4. I have a critical number. So then our final step is going to see if this critical number is a min or a max. So because we are trying to maximize the volume, right? Not minimize the volume. So we're going to go ahead and make a number line, and we're going to say we have a critical number at 4. What's our derivative doing before 4? Well, I always pick an easy number. I pick 0. What's it doing at 0? Well, my derivative is 12 minus 0 at 0, so that's positive. And then after 0, or after 4, it's going to be negative. So that means my function is increasing, right? And remember, my function is what? It's the volume. The volume is getting bigger and bigger and bigger and bigger and bigger, and then it hits a max, and then the volume is getting smaller and smaller and smaller. As the width goes close to 4, it's getting bigger. As the width goes past 4, it's getting smaller. So my function is increasing and then decreasing, which means this is a max. So my max is when the width equals 4. That's a maximum point, right? Well, so what does that actually mean for my function, or for my actual real-world problem, right? Well, if my width is 4, the dimensions of my box, because it asked, what are the dimensions? I have 15 seconds. The dimensions should be width equals 4 inches, or centimeters, length equals 4 centimeters, and my height, if we plug it back in, we would get the height equals 2.